Let's start. So first of all, let me remind you where we are at the moment. So last time we proved that if the covariance kernel is smooth enough, then we can construct the corresponding Gaussian measure, and this Gaussian measure will sit on space of Herder functions with a Herder exponent, which is just a little bit below the Herder exponent for the kernel. With a little bit more work, we can actually prove even stronger result, which quantifies the Herder norm. So I'm not going to prove this theorem. It has several proofs. One of them basically follows the same strategy as before. Another one uses some convolution techniques. But let's assume that omega in Rn open domain, and then we have K positive definite kernel in. So we assume that it's K times differentiable in each variable. And then we define its, so its norm is kind of usual CK norm. So we take maximum of multi-indices of size at most k, and then we take supremum over x and y in omega, and then we take partial derivative of order alpha with respect to x, y beta k x y. And then, of course, we assume that norm of k is finite. So our kernel is k times differentiable with respect to each variable. Then there is ck minus 1 smooth Gaussian field F with covariance K, and moreover, so basically first part is just a small generalization of what we have done before, but important is this moreover part. So if we take any exponent between 0 and 1, then for every closed ball B inside omega, expectation of norm of F inside this ball B and with Herder exponent k minus 1 plus gamma is less than some constant. And this constant depends on a lot of things. It depends on domain, it depends on our ball, it depends on k, gamma. Important thing is that this constant does not depend on the kernel. And dependence on the kernel is this. So what do we have? Before we proved that if the kernel is Herder continuous, then field is Herder continuous. Now we know that if it's more differentiable, if the kernel is k times differentiable, then F is almost k times differentiable. So it's k minus 1 times differentiable, and the last derivative is Herder continuous with any exponent below 1. And important thing is that we know, so now we have kind of uniform control over derivatives. So we know that expected value of this norm is uniformly bounded. And in fact, there are even stronger results.
I have a small question here.
Yes.
So when we talked about Hölder continuity, we defined this with like restricting to a dense set and talking about norm on this dense set.
Yes.
And here, can you elaborate on how we define?
Well, actually, we use this discrete Hölder only inside the proof. Then we pass to the limit. So Hölder norms that I'm talking about, they are absolutely usual Hölder norms. So we just look at supremum f of x minus f of y, x minus y to the power gamma. So we just use standard Hölder norm. But last time when we wanted to prove that the field is Hölder, the problem is that this definition, and it uses valuations at all points, which is hard to work with. So we first discretized and did some computations on a dense, but on a countable dense set, and then we passed to the limit.
Yeah, but here we will need something like this, don't we? And to define derivatives, we would need to work with again something like not on a countable set.
Yes, yeah. I'm not saying that this proof of this is kind of verbatim the proof of the last theorem. So there is a proof which uses, well, you see, kind of, in this case, we have much better smoothness of the kernel, so we have a slightly better control. Probably the simplest proof of this is the following. So you kind of take field, you don't know how smooth it is. You convolve it with some modifier. Now you have obviously very smooth field. Then it's possible to, and then you argue that as modifier goes to delta measure, kernel of kind of smooth field converges to the kernel of the original field, and field with derivatives will be tight. So actually convergence of fields will be uniform enough so that the limit is also differentiable. So strategy, at least one strategy for the proof is like that.
Okay. And so this CK minus 1 smoothness, I should understand as samples are smooth with probability 1.
Well, yes. So we, well, since we can ignore things that are of zero measure, yeah, kind of, yeah, it's with probability 1, or just my Gaussian measure sits only on these things. It doesn't really matter. But yes, so what it means is that with probability 1, sample of this field is k minus 1 times differentiable, and its derivative is Hölder with any exponent less than 1.
Thank you very much.
There is slightly different versions. So sometimes you want fields to be k times differentiable. Then your kernel should be like k plus epsilon differentiable. So if you assume that it's k times differentiable and derivative is Hölder with some Hölder exponent, then fields will be k times differentiable. So basically, if k has certain Hölder exponent, then field has every Hölder exponent below this one. Okay?
Yeah, okay, thank you.
And actually, there is an even stronger result which tells us something about modulus of continuity. This is Dudley's theorem, and it gives us actually an estimate on modulus of continuity. So given covariance structure, there is a natural pseudometric on our space. So we can define the following distance. And then, of course, in terms of kernel, it's this thing that we have seen few times. So this is almost a metric. So it has triangle inequality. Unfortunately, of course, distance between two different points could be zero. So you could have 2 points that are 100% correlated, which is perfectly fine with fields. And then, of course, distance is zero, so it's not metric, it's pseudometric. And then we assume that T, our space, is D compact. So it's compact with respect to this metric, and then we can define. So you see, a priori, our space has no metric structure on its own. Of course, interesting cases when, say, T is also a metric space, but then we have to compare these two metric. We have to compare a metric in T and this new metric. And then we can define, of course, modulus of continuity. Sorry, of f with respect to this metric. So this is just supremum. Sorry, f t where distance between s and t is less than delta. So usual modulus of continuity. And now we need the following parameter, n of epsilon. It's the minimal number of epsilon balls needed to cover T. So we can, so T is compact, so we can cover it by finitely many balls of diameter or radius epsilon. And then we look at this number h of epsilon, which is log of n. And then the following holds. First, expected value of supremum of f over all t is bounded by some universal constant, and then we have this funny integral. So it's kind of an entropy type thing. So we take square root of logarithm of number of balls needed to cover our space, and this gives us a bound for expected supremum. And second, there is some random variable, say, let's call it eta, which is strictly positive and finite, and a universal constant such that our modulus of continuity is less than some universal constant and integral from 0 up to delta h1/2 epsilon d epsilon. So modulus of continuity is a random thing. We have this for delta less than n. So we have some random variable, and which gives us scale. So when delta is less than this scale, then on this maybe a random small scale, modulus of continuity behaves like a function which we can compute explicitly. So in particular, we know we know upper bound for the modulus of continuity, and you can, out of this, you can extract Hölder exponent. Okay? And in particular, if T has metric on its own, so for example, T is a subset of Rn, then of course, you want modulus of continuity with respect to the standard metric. But for this, you have to compare standard metric and this pseudometric, which can be easily done because if you look at this metric, if you know how, if you know that K is is say Hölder something, then it gives you exactly comparison between our pseudometric, which is kind of canonical metric related to the field, how it is related to, say, Euclidean metric on our space. And theorem above actually can be extracted out of Dudley's theorem. It's actually quite a nice exercise derive this quantitative Kolmogorov theorem from Dudley's.
So we can think about this as like adding regularity from the kernel with respect to the usual Euclidean metric and the regularity that is given by these theorems. Yep.
Well, kind of this theorem gives us regularity with respect to this canonical metric related to the field. But if you know that covariance, and this metric is given in terms of covariance kernel. If you can control covariance kernel, then you can control this metric in terms of Euclidean metric. And then, of course, if you have two metrics and you know how to compare them, then you can recalculate modulus of continuity with respect to one metric into modulus of continuity with respect to another metric. Okay?
Yeah, okay.
Okay, now we will need one more important ingredient. So now we know that if our kernel is nice, then expected CK norm is finite. But sometimes we want to control tails. So we want to know that probability that, well, for example, we know that our field is say C1, and then expected, well, say derivative is something. So we have control over it. But what about tails? Because sometimes we want something like this. Say we have a field and we know that its, say, variance is 1 everywhere. So then you expect that your field is everywhere of order 1. But of course, there is a small probability that it will be large. And this is kind of, for us, it will be a bad event. Because quite often we want to perturb one field by another. And if our field is abnormally large, it's a problem. So we want to control events that, say, maximal derivative or maximum of function over some set is much larger than what we expect. Of course, you can do something just from Markov inequality, but it's not good enough. So we need a much stronger decay of tails. So essentially, we want to say that maximum is very large with exponentially small probability. And this is something which is called Borell-TIS inequality. And TIS stands for Tserelson, Ibragimov, Sudakov. There are many forms of this inequality. What I'm going to present is not the strongest one, but it's perfectly fine for our purposes. As I mentioned before, in this course, well, since my fields are very nice, I'm not really after sharpest results. So what we are working with is, say, F is a continuous field on some compact space T. And then we write, so traditionally it's written as a norm, although this is not a norm. So this is supremum of f of t over our space. And then we use another notation. So sigma squared t is supremum of variance, which is, of course, supremum of k tt. Then probability that norm of f minus expected norm of f, probability that this is greater than something is less than e to the minus u squared over 2 sigma squared t, and this is true for all positive values of u. So it means that norm of u, so if you look at maximal value, then the probability that maximal value exceeds expected maximal value, this probability has Gaussian tails. In particular, it decays extremely fast. Any questions so far? Okay, so, and
I just wanted to clarify that from Markov inequality, we would get like polynomial decay of any degree, and here we get exponential, and
yes,
this is way better. Yeah,
yes,
okay.
And also actually this is, well, this is almost sharp. So there are some kind of polynomial correct. So basically up to some very, very small modifications, this is sharp. And sometimes you want not maximal value, but maximum of modulus, but this is not a problem because, of course, probability that supremum of f is large is bounded by twice that supremum of f is large because our field is symmetric. So if you want to control, say, L infinity norm, then it's all the same. And actually, before we prove, I'm going to explain some ideas behind proof. I'm not going to write all technicalities. But before doing this, I want to mention an important corollary, kind of, why do we care? And this is kind of the most frequent application of Borell-TIS in geometric study of Gaussian fields. So again, we assume that we have some domain in Rn. We assume that omega can be covered by, say, n balls of, say, radius 1. Actually, they don't have to be of radius 1, just of some radius. Then we have kernel, which is ck plus 1, ck, sorry, ck plus 1, k plus 1. So our field is k times differentiable, then even a bit better. Then there is some universal constant C1, such that for all a greater than C1, probability that ck norm in omega is greater than a sigma omega is bounded by exponent of log n minus a minus c1 squared over 2. Well, clearly it's not optimal. For example, I don't, well, this can be pushed to, from ck norm, we can look also at Hölder norm of kth derivative. I don't care. So what do we have here? We have this sigma, which gives us expected size of this norm. And then we expect that our field, so kind of all derivatives, are of order sigma. Now, what is the probability that we exceed it by a certain factor? Well, when this factor is very large, it decays like Gaussian tail. But there is a price to pay. If we have very large domain, then clearly, if you have large domain, then there are more chances that somewhere your field will be unusually large. So clearly that if you fix A and send size of the domain to infinity, then this probability will not be small. Because if your space is huge, then somewhere something bad will happen. But we can control this. So this upper bound is small when a is much larger than square root of log n. And so, for example, if omega is ball of radius r, then n is something like, well, r to the power n. So we need r to the power n balls to cover a ball of radius r. And so we need a much larger than square root of log r. So in particular, basically this means that we kind of expect that if you have a nice field, say in Rn, where we have uniform control over covariance everywhere, then in each ball of radius 1, you expect that your field will be of size 1. But if you take a ball of radius r, then there will be some place where your field is of order square root of log r. Okay?
A small question. In the inequality on the previous slide, we don't have k on the right-hand side. Is that right?
Yes, because you see, this inequality is kind of scale-free because we have sigma on the left.
Mm-hmm.
And it's kind of scale-free. So if you multiply k by a constant, then also your field is multiplied by the same constant. And so probability does not change.
What I mean is I mean k, the number of derivatives.
Yes, so this kind of it's hidden in this. So this universal constant is it does depend on number of derivatives, but dependence is kind of not really essential. And also, well, you see, number of derivatives. So when we define, sorry, I haven't mentioned what is this. If we talk about higher derivatives, then this sigma is supremum not only like here, supremum of expectation of f, sorry, not only variance of f, but it's supremum of a variance of f, f prime, and so on. So it's it's a universal upper bound for all derivatives of order up to k.
And so this dependence on k is in this sigma.
Yes. Well, but it's also in this universal constant C1. The same way as in this theorem. So if you look at this constant, which gives us expected norm, there is number of derivatives in this constant.
Yeah, I see. Thank you.
But to be honest, I don't remember what it is exactly, but basically it kind of scales as k or k or square root of k, something like this. So it's not a problem. And when you deal with higher derivatives, it's also easy to do. And yeah, so this is not a problem. Okay?
Yeah, okay, thank you.
Now, let me explain what is the idea behind all of this. And, well, kind of when you look at estimates like this, when you have it, it really looks like a concentration inequality. So there are a lot of these various Gaussian concentration inequalities that if you have, say, for example, a nice functional of a Gaussian, then it concentrates around its expected value, and deviations are kind of, they have Gaussian tails. So behind all of this is the following Gaussian concentration lemma, which I'm not going to prove. But if you have ever seen any kind of Gaussian concentration, then this will look really familiar. So we take Z to be standard Gaussian in Rn. So it's a very simple object, and then we take we consider function h from Rn to R, which is Lipschitz with norm sigma. Then for every positive number, the probability that if we, so now we apply our Lipschitz function to, sorry, this is Z, to our standard Gaussian, the probability that it exceeds expected value by at least u is bounded by e to the minus u squared over 2 sigma squared. So when h is linear, it's absolutely standard Gaussian concentration. When u is not linear but Lipschitz, it's slightly more complicated, but along the same lines. Okay, but important thing is that this is finitely dimensional thing. And the idea of the proof is that it's enough to prove Borell-TIS inequality for finite spaces. So let's consider finite. So there are finite sets T, well, increasing finite sets such that the union is dense in T. So we take, say, countable dense set and approximate it by finite sets. And then it's easy to see that if you look at supremum of F, when you take supreme over Tn, it converges almost surely to supremum of F over the entire space T. This is because our function is monotone. Oh, sorry, this is continuity. And this convergence is monotone. Okay? So supremum, basically supreme over dense set is equal to supreme over the entire space. And also what we have is, well, this implies that if you look at probability that supremum over Tn exceeds some value, this converges to the probability that this supremum exceeds some level, and expected value converges to expected value. This is, well, since our convergence is monotone, we can pass to this kind of, we have these limits. And also, of course, sigma converges to sigma. So what does it mean? It means that if we can prove our TIS inequality for finite space, then by passing to the limit, we have it for the entire space. And next step is just a simple observation that well, there is a matrix A, which is just the square root of covariance, such that F, now we're dealing with finite dimensional case. So F is just a Gaussian vector in Rn. And as we discussed before, there is matrix such that F has distribution of A Z, where Z is standard Gaussian. But then it's easy to argue that maximal component, so now we are interested in maximum of Fi over all coordinates. This is maximum of AZI, and with a little bit of linear algebra, you can see that maximum of AZI over I is a Lipschitz function of Z with norm equal to maximum of CII. And we're done. So that's the idea behind the proof of Borell-TIS. Okay? And I think that's a good time to have a couple of minutes break, and we'll continue after that. Okay, so maybe let's move on. And now let me introduce one more important technical tool, which is usually known as Bolinskaya lemma. The idea is very simple. So let's assume that we have a nice Gaussian field. So F is a Gaussian field, but now it's not real valued, it's vector valued. So F is Rn plus 1 dimensional in omega, which is n dimensional. So we have n plus 1 Gaussians, in n-dimensional space, then what we expect is that f has no zeros. And we expect that this is true under some regularity condition. And this is kind of basically very natural. So in general, if you think in terms of kind of nice functions, so if you have n+1 functions in Rn, you do not expect them to have a point, to have a kind of common zero. And it's quite easy to show that if you fix one point, then probability that field vanishes at this point is zero. But what is more difficult is to show that the same is true simultaneously for all points, because we have uncountably many points. And I will formulate slightly different versions, so because we will care mostly about function and its gradient. So what we will have is that assume that f is C2 minus, well, C2 or C2 minus Gaussian field. Such that f and its gradient is a non-degenerate Gaussian field. So the joint distribution is non-degenerate. Then 0 is not a critical level with a probability 1. In other words, almost surely there is no x such that f of x is 0 and gradient of f of x is 0. And the idea of the proof, again, I'm not going to prove it, but the idea is this. So
can I have a question?
Yeah,
To
sure.
the proof? You said that so if we fix some point, then the probability of having n+1 zeros at this point is 0. I just trying to understand.
Well,
so we have absolutely continuous random variables here, and the probability of any single value is.
Yeah, sorry. Stronger thing holds. So basically, if let's forget about 0, let's take some small value. But basically, what happens is that if you fix some small neighborhood, then joint density around 0, then since you want n+1 things to be small, like of order, say, epsilon, it will be like epsilon to the n+1.
So the assertion is about being small in some neighborhood of some point. Yes.
Yes. So this is what will really happen. So you see, if we let's talk about, say, one-dimensional case. So if you have just a Gaussian field, say smooth Gaussian function in R, then of course, if you fix a point with probability 1, this point is not zero of your process. But for most processes, there will be zeros somewhere. But if you want simultaneously f and f prime to be zero, then this will not happen. And I will explain in a moment basically what is behind it and its regularity of our field. So the idea is that if function and its gradient are simultaneously very small at some point, then since our field is regular, they are also very small in a neighborhood, and that will be a problem. So let's consider this event. So let's look at some compact in omega, and then we look at this event, that there is some point in this compact such that this is zero and gradient is zero. Then let's take, so this is omega, this is our Q. Then of course there is some distance between Q and boundary of omega. And then we have that f and gradient f are, say, beta Hölder. For some, well, actually for any beta less than 1. And then it means that, so if you have this point Z and you take disk of radius delta, then for every x in this ball, we know that f is cannot be more than x minus z, because we have a finite gradient, and gradient cannot be more than x minus z to the beta. So we have control over this. And now let's look at the following function. So it's f to some power minus alpha and gradient to minus alpha n, and here alpha is just some number between 0 and 1. Then in this ball, what we have is that f is kind of at least z minus x to minus alpha 1 plus beta n. Okay? And then what we have is that if we choose parameters so that alpha 1 plus beta n is more than n. This can be done. So we can choose alpha and beta less than 1, but close enough to 1 so that this is more than n. And then it means that integral of phi over omega diverges. Okay? On the other hand, let's look at the expectation of this phi. But now, what happens is that, well, actually for fields that are stationary, this is exactly true, that f and gradient f are independent, but for other fields, well, this is our non-degeneracy assumption, since, well, basically, this part is integrable, and this part is integrable, because alpha less than 1, and so expected value is finite. So expectation of phi is finite. But integral of phi over space is infinite. But now we use Fubini, and it gives us, so since integral is infinite but expectation is finite, it means that measure of this event is 0. And then we cover our space by countably many compacts. So that's the idea. Alternatively, you argue that if simultaneously function and gradient are small, then you have disk where you have control. You cover your space by small disks. Then if in one of these disks f and gradient are 0, then in the center of this disk, f and gradient are small. And then you estimate the probability that, well, basically, if you have these disk of size epsilon, then in n-dimensional space, you need 1 over epsilon to the n disks, but probability that in the center both f and gradient are small is epsilon to n plus 1, and so expectation of this, measure of this event is small and goes to 0 when epsilon goes to 0. So there are different ways. And moreover, there are quantitative versions of this lemma. Instead of proving that f and gradient of f cannot vanish simultaneously, we can show that probability that there is a point where they both are small, probability of this event is small, and we can quantify all of these. Okay, now why do we need these? In some sense, we need it for the following reason, which is, so now I want to explain another technical tool, which is actually an extremely powerful tool. And this was, to a large extent, up to 10 years ago, that was the most the only and the most powerful tool in all results about level lines of Gaussian fields. So this is something which is called Kac-Rice formula. And this is, in fact, something which is extremely natural. And let me start with a deterministic one-dimensional thing. So you have some function on an interval a, b. And we assume that f is, say, C2. And, well, we assume that endpoints are not roots. Well, you can fix it. And then we also assume that 0 is not a critical level. So you assume that all zeros are simple. And now what we want to do is compute number of these roots. And you can do it in the following way. So let's take epsilon neighborhood of 0. And now we get these intervals where function is below, well, modulus of f is epsilon small. Then what is length of this? So length of this interval is approximately 2 epsilon divided by f prime. So what is the conclusion? If we integrate from a to b characteristic function of modulus f less than epsilon times modulus of f prime, then integral, since derivative is not 0 and derivative is also, we have control over derivative. So it means that integral of this thing over each interval is about 2 epsilon. So if we normalize by 2 epsilon and pass to the limit when epsilon goes to 0, we get number of roots. So very simple deterministic observation. Now, what happens if f is a Gaussian field? So we have Gaussian process in R. Then, again, I will assume that we can swap all limits, like integrals, limits, expectation. Then expected number of roots of f in this interval, maybe let's just write AB, will be integral over I, and then we have this limit of 1 over 2 epsilon, and then we have integral from minus epsilon to epsilon, expectation of f prime, well, modulus of f prime of t conditioned on f of t equal to u. Then we have density of f of t of u du dt. So we kind of integrate, so we have density that f is equal to u, and then we take conditional expectation of modulus of derivative given that f is equal to u. And then we want to pass to the limit. And then when you pass to the limit, what you will get is integral over this interval of expected value of modulus of f prime of t conditioned on f of t equal to 0. Then we have density of density of f of t at 0 dt. Okay, so far so good. And now, what is the nice thing about Gaussians is that if our field is Gaussian, then its derivative is Gaussian. And we can write the joint density. So f prime of t, f of t is actually centered Gaussian. And what is the covariance kernel? Well, it's again not hard to argue that if you look at, say, expectation of f prime of t f of s, then this is dt expectation of f of t f of s. So this is just our covariance kernel. It's the derivative of covariance kernel. So what we'll get here is central Gaussian with a covariance matrix like this. K, so it's derivative with respect to first variable, derivative with respect to second variable, and then you evaluate it on the diagonal. So this is the covariance kernel of this two-dimensional field. And then remember, last time I mentioned this formula, Gaussian regression, so we can explicitly compute these things. So the law of f prime, given that f is 0, this is centered Gaussian, and its covariance is k11 minus k10 squared over k. This is what you get out of Gaussian regression. And then, of course, this is the same as, so when you write this as k11 minus k10 over k, on top, what we have is just determinant of the original covariance matrix. So this is...
There is square missing on above k10.
Yes, thank you. So this is just a Gaussian, but now its covariance is determinant divided by k. And then, of course, what is density? Density of ft at 0 is 1 over, so it's square root of 1 over 2 pi and k. And so what we have is that expected number of zeros on an interval is an integral from a to b, 1 over square root of 2 pi k, and then we need, so f prime condition, so it's Gaussian, and we need expected modulus. Well, this is standard computation. If you have a Gaussian random variable, what is expected value of its modulus? Well, it turns out to be square root of 2 over pi times variance, times its variance. So what we get is square root of 2 over pi, and then we have delta over k. So this is 1 over pi integral square root of delta over k dt. So as you can see, we have a very simple formula. If I give you a covariance kernel, you can easily compute expected number of zeros. And with a little bit more work, if instead of say expected number you want, for example, variance, then you get a simple thing, but you will get double integral, and well, you will integrate much more complicated thing, but it's still something which can be explicitly written in terms of the covariance kernel. And there are a lot of generalizations. So basically what happens is that if you have a Gaussian field, like n-dimensional, and you have another field, sorry, this is n, and you have this, and then you have f in omega, which is in Rn, and you throw in some regularity assumptions that I don't want to write down. Then expected number of points such that f of x is equal to u and g of x is inside some domain B is given by integral over t, and then you have expected, and you have determinant of gradient of f. Well, there is density of f of x at u dx. So you get formula like this, so it's kind of natural generalization. Let me just give you an example. So initially, these formulas were developed to compute number of roots of random polynomials. So this is an example. This is what is called a Crossland polynomial. So if you take a polynomial Pn of the form a naught plus a n x to the n, where a k's are centered Gaussians, but their variance is given by binomial. So how many roots does this polynomial has? So it's easy to compute covariance. So covariance kernel of this is just 1 plus xy to the power n. And then this determinant that I mentioned before will be n 1 plus x squared to n minus 2. And so expected number of roots is 1 over pi. And now we look at roots in the entire real line. It will be root of n 1 plus t squared to n minus 2, and k is 1 plus t squared over n. And this is just square root of n. So for this random polynomial, well, random polynomial of degree n has n roots, but how many of them are real? Well, in this particular case, about square root of n roots well, on average, square root of n roots will be real. More complicated computation. So if you look at what is known as Kac polynomial, and this is, by the way, the first application of Kac-Rice formula. You take the most simple model for random polynomials. So Pn is a0 plus an x to the power n, where ak are independent standard Gaussians. Then again, you can write explicitly covariance kernel, but the formula will be, well, you cannot explicitly integrate these things, so you also have to do some asymptotic analysis, but what you can get out of it is that expected number of roots behaves like 2 over pi log n. So if you take Kac polynomial, then very few roots will be real. Only kind of log n roots will be real. If you take Crossland polynomial, then square root of n roots will be real. Then there is a version with Legendre polynomials. So if you take Pn, which is sum of ak, pk up to n, where p tilde k are normalized Legendre polynomial, and ak are standard Gaussians, then expected number of roots behaves like n over root of 3. So for these polynomials, actually, fixed portion of roots is real. Any questions about these?
Maybe you can comment on why this estimating number of roots of polynomials is important, interesting, and
well, this is kind of one of approaches to kind of one of uses of random functions. So you want to say something about, say, polynomials of degree n. So you ask this question: where are roots of a typical polynomial? Then, of course, you have to specify what does it mean typical. And one way of doing this is saying, like, let's take some probability measure on space of polynomials and pick one polynomial at random with respect to this law. And then we can say something about kind of typical behavior. Okay?
yep. And can we do something with if coefficients would be uniformly distributed, just as a matter of curiosity?
Yes, yes. These can, so basically, these random polynomials have been studied to death. You can work with more complicated distributions. You can even work, so there are even some results that cover when coefficients are not independent but weakly correlated. You see, the beauty of Kac-Rice formula is that if you look at this, it's not really about Gaussian process. So I use Gaussianity to I need Gaussianity to explicitly compute this conditional expectation.
Mm-hmm.
Because for Gaussian things, we have this very nice Gaussian regression. But if you have some other law, you still might be able to compute this thing, or at least estimate it. Of course, if you have more complicated law, then computing this conditional expectation might be more complicated, but in theory, there is nothing impossible. So
Yeah,
Kac-Rice formula is not really about Gaussian process, because you see, it's true deterministically. So it's just computations become a bit nightmarish. But if you don't really care about explicit answer, but you want some asymptotic, then this works kind of in many cases.
Okay, thank you.
And then also this can easily be generalized to higher dimensions. So for example, if you have field F, say from R2 to R, then set where F is 0 will be kind of made of certain nice curves. And this is exactly where we use Bolinskaya. So Bolinskaya lemma, which tells us that 0 is not a critical level, tells us that with probability 1, we never have this. So remember, in this original formula, we cannot deal with multiple roots. So Bolinskaya lemma tells us that with probability 1, it does not happen. So then you can compute. Kac-Rice will give you expected length of these zero sets. Okay. Any questions? Okay. So and now let me mention that best fields or fields that are easiest to study are so-called stationary fields. So it means that law of f of t, well, kind of entire collection, is equal to the law of shifted function. And then, of course, in terms of covariance, it means that k of tx, sorry, of ts is the same as covariance of t minus s 0. And then, abusing notations, I will use the same letter for this function of one variable. And we still call this function covariance kernel of the process. So if our covariance is of this form, then our field is stationary and the other way around. And then there is a very nice result from Fourier analysis that, so this function is positive definite. So, and then the following holds. A bounded continuous function k is positive definite if and only if there is a symmetric Borel measure rho, well, positive, such that k is the Fourier transform of this measure. So this is just Fourier transform of this measure rho. So kernels of stationary processes are exactly Fourier transforms of positive symmetric measures. And symmetric means that rho of A is equal to rho of minus A. And this measure rho is the spectral measure of our process F. So now kind of sometimes it's useful to describe field not in terms of its covariance kernel, but in terms of its spectral measure. But of course, it's absolutely equivalent because spectral measure and covariance, they're just related by Fourier transform. And now it actually gives us another way to describe our Cameron-Martin space H. So if you take space L2 H rho, this is complex L2 with respect to rho and functions H such that H of minus X is equal to, so it's kind of, this is called Hermitian functions, so they have this symmetry, and if you have a Hermitian function and you have symmetric measure, then Fourier transform will be real. Then H, our Hilbert space H, is just Fourier transform of L2H rho. And by this, I mean not only kind of element-wise, but also it preserves Hilbert structure. So this is how you construct this canonical Hilbert space for a stationary field. So it's just Fourier image of L2 space with respect to the spectral measure. And
So,
yeah.
do we mean that Fourier transform is isometry?
Yes,
here?
yes, exactly. So F is isometry L2H rho to H. Yes.
Doesn't this imply that L2H should be reproducing kernel Hilbert space as well?
Yeah, yes.
Can L2 always have
Sorry. No, it does not. So, okay, so let me explain what happens here. So if you have, say, you take psi I orthonormal basis in, say, H, and then psi I, the Fourier transforms of phi I, then of course orthonormal basis in L2. And then what we have is you can consider this is a normal process in L2. So you take W, which is white noise in L2H, Okay?
Mhm.
So formally, it's sum of AI phi I. And then our field is Fourier transform of this white noise. And formally, what is Fourier transform? Fourier transform is you just apply, so this is informal. But formally, this is, so if we call, this is W applied to e to the 2 pi I x dot. So f of x is just white noise applied to exponent.
Mhm.
But, sorry, just, yeah. And then, of course, when you look at covariance, you will get, so if you take covariance f of x, f of y, then it kind of by definition, so remember that is a normal process, is process such that covariance of w applied to a function is e to the 2 pi I x dot e to the 2 pi I y dot, and this product is in L2 rho, right?
Mhm.
And then what we get is, by definition, it's e to the 2 pi I x minus y t 0 of t, which is Fourier transform of rho evaluated at x minus y,
Mhm.
which by definition is k of x minus y. Yeah.
Yeah, so actually I understood that my question was kind of stupid because every Hilbert space is a metric to like L2. And yes, this doesn't imply that it's reproducing kernel Gilbert
Yeah,
space.
so, but yeah, kind of, the issue is kind of, yeah, whether valuations, so Hilbert space is reproducing Hilbert space if valuations are continuous.
Mm-hmm.
So you see, this is yeah, kind of. So of course, in L2, valuations are not continuous. And this is actually why this white noise. So you do not expect this to be a function.
Mm-hmm.
It's a random distribution. But it's a random distribution such that its Fourier transform is a nice function.
Yeah, okay.
Make sense?
Mm-hmm. Yes.
And let me just go over time by just 1 more minute. I want to give two most important examples of this stationary field. One is when k is equal to this. So it's easy to check that Gaussian function is positive definite. And then, of course, rho is e to the minus t squared over 2 dt. And this is what is called corresponding field, is called Bargmann-Fock field. And another important example is field where k is, so it's all in R2. K of, now I write it in polar coordinates. but you should think that it's two-dimensional, or maybe. So this is just Bessel function, or maybe, sorry, let me just write x. It's zeroth Bessel function of modulus of x. And then rho is d theta over 2 pi. So what I mean by this, rho is the normalized arc length on the unit circle. So it's a singular measure, so it's kind of one-dimensional measure sitting in R2. And next time we'll talk a bit more about these fields. Okay, sorry for going over time. Are there any questions? Okay, then that's it for today. And as yesterday, so I will be available on this channel for next hour if you have any questions. Thank you. Bye.